Alright, today we're going to talk about relations and functions. And before I talk, let me say that I'm getting over a cold, so if my voice sounds funny, please pardon that. Now if I were you, first I'd take a moment and begin what I've outlined. So go ahead and write down some of this, pause the video to do that. Alright, let's get started. First we need to know what a relation and what a function is. So relation is a comparison between two sets of numbers or objects. So let's write that. A comparison between two sets of numbers or objects. So for example, we've seen ordered pairs before. And those are put in parentheses and we always list X and then Y. Or you'll also see these ordered pairs on a coordinate plane, which is what I've sketched right here. And there's a couple of things we want to label on this coordinate plane. You'll hear me talk about the different quadrants of the coordinate plane. This is quadrant 1, and we like to use Roman numerals with that. Top left is quadrant 2, bottom left is quadrant 3, and bottom right is quadrant 4. So again, in case you don't know your Roman numerals, we've got 1, 2, 3, 4. It's also helpful to know this dot in the middle is called the origin. And the ordered pair for the origin is 0, 0. This vertical line, up and down, that's our y-axis. And the horizontal line, left and right, that's the x-axis. So that's a relation. Any comparison between two sets of numbers or objects. A function is a type of relation. It's a relation that pairs each element of the domain, which our domain is our x's, with exactly one element of the range. And the range is going to be our y's. So when you were looking at ordered pairs or a table or a mapping, to figure out if it's a function, you need to look at all the x's. All the x's must be different. Okay, if you're looking at the graph, we have this handy thing called the vertical line test, where you draw a vertical line that's up and down, or an imaginary vertical line on the graph, and if it intersects the graph you have more than once, then it's not a function. So intersect meaning it crosses at any point. That's intersecting. So if it intersects the graph more than once, not a function. So it would be really helpful to look at some examples. So take a moment, pause, write down these examples, make sure you have some space to write whether it's a function or not. Alright, let's look at this table. We got our x's on our left, y's on the right. We got 2, 5 is 1 point. We got 6, -3, 8, -1, 9, 2. Well, all the x's and the y's are different, so this is definitely a function. Okay, here's a mapping. And on mappings, it's important to note on the left is always x, on the right is always y. So if I were you, I would label it x and y. But just know that in tests and stuff, they usually don't label it. But you might want to do that for your notes. This one's x, this one's y. Okay, we got 3 and 2 on the x side, and then 1, 7, 8 on the right. But look, we have 3 goes to 1, and it goes to 7. That's not allowed. So this is not a function. Okay, now we got two graphs. So the bold is our actual graph. So let's pretend we have a little vertical line. So this is going to be my vertical line. If we pass it all over that graph, it only hits it one point at a time. So this is a function. But here's a new graph. When I do a line here, look, right here, I'm passing through it 2 times. 1, 2. I intersect my graph twice. So this fails the vertical line test. It is not a function. Because again, it hits the graph here and it hits the graph there. That's twice, and that's not good. All right. Our last example is ordered pairs. We've got 2, -1, 3, -1, 5, 5, 7, 2. So look at your x's. We got 2, 3, 5, and 7. Are any of those the same? Nope. So this is a function. Again, because we got to look, the x's got to be different. They are, so we're good. Okay, we're on to page 2. So if I were you, go ahead and pause, write what I have so far, make sure you leave room to draw on these graphs, don't make them tiny. And Dixie-Royd is an acronym, so leave space for some words. Okay, all functions, they can be increasing or decreasing. To decide if it's increasing or decreasing, you just gotta kind of read them. So go left to right. So for example, if we have this line, nice dark line, this is an increasing function because going from left to right, we're moving up. So moving left to right, moving up. Well, it doesn't have to be a line, it could be a curve. So if this were our function, again, look, going from left to right, we're moving up, so that's increasing. The opposite would be decreasing. So here's another line. And always go from left to right. So going from left to right, we're going down, so that's decreasing. Or again, you could have a curve. And always going from left to right. That one's decreasing as well, left to right. And notice it might look like it kind of levels out. That's okay. It's still decreasing overall. All right, let's talk about our friend Dixie-Royd. Dixie-Royd is how you can remember the domain and the range, and what all is associated with the domain and what all is associated with the range. So D in Dixie stands for domain. The domain is also related to our input. Our input are our x values, and x is always the independent variable. Okay, Royd, our other word, that's how we remember the range, what's associated with the range. The range is associated with the output. Oop, I have too many O's, don't I? Aha, not output. Output, there we go, that's much better. And that's going to be our y values. And finally, our y values are the dependent variable. So when I say input and output, think of like a machine. So I don't know if you've ever seen cotton candy being made. It's really fun to make. If you get a chance to make cotton candy, do it. So you put in this sugar stuff, this sugar powder, and you turn on the machine. So our input is that sugar, and then you spin it around, and our output is this awesome cotton candy. So think of it that way. Input, what you put in, output, what you get out. Now to decide what's dependent and what's independent, that can be kind of tricky. So we like to use a dependency statement. Ask yourself, how can you word it so that blank depends on blank? The first blank is your dependent variable. Your second is your independent. So for example, your average in my class depends on your individual grades. So your overall average is the dependent variable. Each individual grade, that's independent. All right, a little more. So again, I suggest you pause, copy this down, make sure you leave the blanks where I wrote them. Let's talk about some graphs. So there are two ways we can describe graphs. They can be discrete or they can be continuous. And if you look way back in your notes, I think the first notes we took, we made a note of discrete and continuous. So discrete is a relationship involving countable whole quantities. So countable whole quantities. So you're not going to have 3.2 or 8.9. So think of dots. So when you see discrete, think of dots. Note They both begin with the letter D. So when I say dots, I mean they're going to be parts and pieces. And so think of like a little graph. You don't have to draw this. If you see like little dots like this, that's discrete. Ooh, that did not show up well. Little dots like this, that's discrete. Okay. Continuous, that's when your data points can be connected. So when you see continuous, think connected. Both begin with C. And they're going to form a line or a curve. So when I say continuous, think connected. And in fact, if you look back up here, these are all continuous. Because notice how it's all connected. We don't see any dots. All right, let's practice figuring out whether stuff is continuous or discrete, what's the dependent, what's the independent. So let's do some biology. Most of y'all are in biology class, so let's do that as an example. So the rate of plant growth is related to how much light it gets, its light exposure. So ask yourself, can we say plant growth depends on light exposure, or light exposure depends on plant growth? Well, I think it makes more sense to say plant growth depends on light exposure, because that light is not going to change just because your plant gets bigger. That doesn't make sense. So plant growth, that's our dependent. So our X. That means our light exposure, oops, I said that wrong, didn't I? Dependent is Y. Duh. Our light exposure is the independent, X. Glad I caught that in time. And what do we think? Could that be continuous? Could we have some plant growth? Would it have to be, 1 foot, 2 foot, 3 foot, or could we have 1.5 feet? Well, I think we could have 1.5 feet, so that'd be continuous. And same thing with light exposure. You can get 3 minutes of light exposure, 3.59, all that. All right, our second example, study time and grades. So, does your study time depend on grades, or do your grades depend on the amount you study? Well, I think your grades depend on the amount you study. So that means our dependent is our grade. That's our Y's. And the study time is the independent variable, or the X's. Now we got to ask ourselves, okay, is this going to be discrete or continuous? And this is a really tough example, I'm going to be honest, because yeah, we can study for 3.5 hours and 4, and we can get grades of 89.2. But think of it this way, if we have lots of different people, if I study for 2 hours for math, is my grade going to go up as much as your grade if we both study for 2 hours? Probably not. If I study, it might go up by 5 points for an hour. Yours might go up for 10 points. So it's going to have this shifting. It's not going to be all connected, because sometimes studying for just 5 minutes gives you a tiny boost, but then maybe studying for 10 gives you this huge boost, and it might bump up and down. So I would say this is discrete, because we'd have dots everywhere, and they wouldn't necessarily make one smooth curve or a smooth line. All right, you should have some practice. Let me know if you have any questions.